So continuing on with our discussion on force and motion, let's look now at a few examples on force analysis. So we have the following problem. A string is tied to a box A and passed over a frictionless pulley. Box B is attached to the other end of the string and is suspended from the pulley as shown in the figure. Box A has a mass of 2.5 kilograms. If the coefficient of static friction between box A and the table is 0.75, what is the maximum mass that box B can have and still have the system in equilibrium? So here you see the problem. Figure is already provided. So we don't have to draw the system from the problem. We can go to the next step of force analysis, identify the forces in the system. Here we have two objects, box A and box B. So we look at the forces affecting each object. For object A, it has mass, so it has a vertically downwards weight. Object A is placed on a surface, so it is pressing into the surface. Due to its weight, the surface will react by producing a vertically upward normal force. Vertically upward because the surface is horizontal. Object A is being pulled by the string, therefore it is experiencing the tension due to the string. And since A is being pulled to the right, it will be sliding, or it's potentially going to slide to the right on the table surface. Friction will arise to oppose this sliding motion. Object A is simply resting on the table, therefore the type of friction that will arise is static friction. Static friction will be horizontal, heading towards the left. Next, we have the forces on object B. B also has mass. That's what we are looking for. Therefore, object B also has weight heading vertically downward, and object B is being pulled up by the string, so the string will apply a tension heading vertically upward. So these are the forces acting on our objects. Next, we go to the following step. Draw the free body diagrams and then analyze the free body diagrams using either F net is equal to 0 or F net is equal to MA. We have two objects, box A and box B. Each object will have its own free body diagram. Let's go to box A first. The free body diagram for box A is as shown. You have four forces. Weight A vertically downward. The normal force between box A and the table vertically upward. The tension in the string pulling A to the right. And opposing the impending motion, static friction heading towards the left. So you have weight A, N, T, and F sub S. Now the problem tells us that the system is in a state of equilibrium, therefore F net is equal to 0. Therefore, F net is equal to 0, equilibrium. Definition of F net, summation of all the forces acting on the object. F net is equal to F sub S plus N plus T plus weight A. Using now our X component, we analyze the equation. First, we look at X component. F net x is equal to 0. X component of 0 is still 0. Is equal to negative f sub s. F sub s is heading to the left, negative direction. Plus 0 plus t. T is positive direction. Plus 0. Here, the normal force and the weight A both have 0x components because these two forces are vertical. They don't have x component. The x component equation therefore tells us that the magnitude of tension is just the same as the magnitude of the static friction. And we know that static friction magnitude ranges from 0 to mu sub sn rather. Static friction has minimum and maximum values. Tension therefore also has minimum and maximum values. Minimum tension is 0, maximum tension is mu s n. Going now to the y component, F net y is equal to 0 because y component of 0 is still 0. And then summation of all the forces, y component, F net y is equal to 0 plus n plus 0 minus WA. This time, static friction and tension have 0 components because they are horizontal. They do not have y components. Only the normal force and the weight A have y components. Our y component equation tells us that the magnitude of the normal force is just equal to the magnitude of weight A, and we know magnitude of weight A is just MAG, which gives us 24.5 newtons. We know that the maximum value of the tension is mu s n. Knowing that n is equal to 24.5 newtons, we are now able to calculate the maximum value of tension. T max is equal to 0.75 times 24.5, 0.75 being the coefficient of static friction given by the problem. T max is equal to 18.375 newtons. Next, we move on to the second object, box B. Box B has two forces acting on it. Therefore, it has the following free body diagram. It has weight B vertically downward and tension T vertically upward. Notice that there's only one tension in both the free body diagram for A and the free body diagram for B. That's because there's only one string and there's only one tension in the string. So the tension in the free body diagram for A is also the same as the tension in the free body diagram for B. And again, the system is in a state of equilibrium. Therefore, F net is equal to 0. But this time, for object B, F net is equal to tension plus weight sub B. Going now to the x component, both our vectors T and WB are vertical, therefore no x component. We move on to the y component. F net y is equal to 0. Y component of 0 is still 0. Tension is heading in the positive direction and the weight is heading in the negative direction. Therefore, F net y is equal to T minus weight sub B is equal to 0. This means that the magnitude of weight sub B is just equal to the tension. Weight sub B magnitude is MBG. Therefore, MB mass of box B is just equal to tension divided by G. If we set the tension to maximum, you have maximum mass for object B, for box B. MB max is equal to T max divided by G, which gives us 1.875 kilograms. Okay? Not meters. M is wrong here. It should be kilograms. kg. So 1.875 kilograms. So moving now to the next problem. You have a string tied to box A and passed over a frictionless pulley. Box B is attached to the other end of the string and suspended from the pulley as shown in the figure. Box A has a mass of 2.5 kilograms while box B has a mass of 3 kilograms. If the coefficient of kinetic friction between box A and the tabletop is 0.6, determine the acceleration of the system. So as you can see, this problem is similar to the previous problem, except that this time the mass of box B is given, and instead of equilibrium state, the system seems to be in an accelerating system. The system seems to be undergoing acceleration, and the problem is asking for the value of that acceleration. Since the system is similar to the one shown in the previous problem, it's not surprising that the same forces will be involved. We get basically the same free body diagrams for box A and box B. The only difference here is that there is acceleration to consider in our analysis. For the system to accelerate or move, there are two possible directions that A can move. A can move to the left, slide to the left, or slide to the right. Whereas B, there's only two directions. It can either go down or up. Since A and B are tied together, they will move together. If A moves to the left, B must move upward. If A moves to the right, B must move downward. Since B is being pulled downward by its weight, there's only one possible direction for the system to move. A will move to the right and B will move downward, which means the acceleration of the system is moving in this direction. A will accelerate to the right and B will accelerate downward. Analyzing first the free body diagram for object A, you have weight A vertically downward, normal force vertically upward. This time, the system is already moving, so instead of static friction, you have kinetic friction heading to the left and tension heading to the right. And A is accelerating to the right as shown in the free body diagram. Since the system is accelerating, F net is equal to MA. And F net is summation of all the forces acting in the system. So that means you have MA is equal to FK plus N plus T plus WA. If we are then to use our X and Y components, X component, MA is equal to negative F sub K plus 0 plus tension plus 0. Again, normal force and weight A are vertical, no X component. And this gives us basically T is equal to MA A plus F sub K. And F sub K is constant at mu K n. Therefore, T is equal to MAA plus mu k n. Going to the y component, the acceleration is horizontal, therefore no y component. So MAA is 0 in y component. So you have 0 is equal to 0 plus n plus 0 minus WA, meaning normal force magnitude is just equal to the weight A magnitude. Weight A magnitude is MAG. Normal force magnitude and therefore is just equal to 24.5 newtons. Going now to the second object, box B, you have the following free body diagram. You have vertical tension upward direction and vertical weight downward direction, weight B. And the acceleration of object B is vertically downward. Analyzing now using Fnet. Fnet is equal to MA because the system is accelerating. So Fnet is equal to M sub BA, and Fnet is summation of the forces. Fnet is equal to T plus weight B. Analyzing now using our component method, all the vectors are vertical, therefore no x component. We go directly to the y component. Y component, F net y is equal to negative m sub BA is equal to T minus weight B. Positive direction is upward, negative direction is downward. We know that T is equal to M sub AA plus mu k T from our analysis of the free body diagram for box A. Combining that equation with our equation here in free body diagram for box B, and simplifying, we get an equation for acceleration A. A is equal to mbg minus mu kn all over ma plus mb. Plotting in the values, we know all the values except for A. We are able to calculate the acceleration of the system. A is equal to 2.673 meters per second squared. And that's pretty much it for our discussion on the examples of force and motion, examples of force analysis. That's it for our discussion on force and motion. So thank you for watching.